Hey there! Let's talk about something that powers, well, everything around us, electricity. We're going to pull back the curtain on this invisible force and break down the simple ideas that make our modern world tick, from the phone in your hand to the lights in your room.
So here's what we're going to cover. We'll start with the big picture. What is this invisible flow? Then we'll get into what electric current actually is, what gives it a push, and the golden rule, Ohm's law, that ties it all together. After that, we'll see what slows it down, and why some materials are conductors and others not so much.
Okay, let's get right into it. Think about a simple action you do every single day, probably without even a second thought. You flick a switch and boom, instant light. It feels like magic, right? But it's not. It's just some really cool physics. What you're actually doing is completing a path, basically giving an invisible force the green light to flow and get to work.
Now, to wrap our heads around this invisible force, we're going to use one simple, powerful analogy. Think of electricity as water flowing through a pipe. It's that simple. We're going to come back to this idea of water in a pipe again and again because it makes everything else just click.
All right, so if electricity is like water in a pipe, what exactly is the flow we're talking about?
Well, that flow is what we call electric current. And really all it is the rate that electric charges, tiny little particles like electrons, are moving through a conductor, like a wire. It's all about how much is flowing and how fast.
And this right here is the secret to that light switch. For the current to flow, it needs a complete unbroken loop, what we call an electric circuit. When you flip the switch to on, you're closing that loop. You're making the path whole. Break that path, flip the switch off, and the flow stops. No more light.
So how do we measure this flow? We use a unit called the ampere, or just amps for short. Now, 1 amp means that 1 coulomb of charge is flowing past a point every second. And a coulomb, well, it's just a massive number of electrons. So think of amps as a way to count how many electrons are zipping by each second.
And this isn't just some abstract science concept. To put it in perspective, a simple little light bulb using just half an amp for 10 minutes. That means a staggering 300 coulombs of charge have flowed through that tiny filament. It's a huge amount of movement happening on a microscopic level.
Okay, so we've got these charges flowing, but why are they flowing? I mean, water won't flow through a flat pipe by itself, right? It needs a push. And it's the same for electricity. And this is where our water pipe analogy is just perfect. Think about water pressure, right? It's what pushes water through the pipes. Well, electricity has its own version of pressure that shoves those charges along. The fancy term is potential difference, but you definitely know it by its everyday name, voltage.
That voltage is what you get from a battery or a power outlet. It's the oomph, the force that gets the current moving. We measure it in volts, and it's pretty simple. More volts means more push.
Okay, this is where it all starts to come together. There's a beautiful, super simple relationship that connects the push and the flow. A German physicist named George Ohm figured it out, and it's kind of the golden rule of electricity.
Way back in 1827, Ohm discovered something incredibly elegant. He found that the push, the voltage, is directly proportional to the flow, the current. What does that mean? It means if you double the push, you double the flow. It's that straightforward.
And he boiled this whole idea down into one of the most famous equations in physics, V equals I times R. Voltage equals current times resistance. This is Ohm's law. And I'm not kidding, it is the absolute cornerstone of, well, pretty much all modern electronics.
Wait a minute, what's that R we just added? That, my friends, is resistance. Let's go back to our pipe. Resistance is like a squeeze or a pinch in the pipe that makes it harder for water to get through. In electricity, it's a material's natural tendency to fight against the flow of charge. And yep, we measure it in ohms.
So if resistance is the squeeze in the pipe, what determines how much squeeze there is? Well, it turns out it comes down to a few basic physical things.
First up is length. Think about it. It's a lot harder to push water through a really long winding hose than a short one, right? Same deal with wires. A longer wire means the electrons have a longer, tougher journey. So longer wire, more resistance. Simple.
Next up, thickness. A big, wide fire hose can move a ton of water, no problem. A tiny little straw, that's a bottleneck. It's the exact same thing for wires. A thicker wire gives the electrons more room to move, so it has less resistance.
And the last piece of this puzzle is the material itself. I mean, not all pipes are created equal, and for sure, not all materials handle electricity the same way. This gets us to the big difference between conductors and insulators.
Every material has this built-in property called resistivity. And what's wild is the difference between materials. I mean, look at this. A great conductor like silver basically puts up no fight at all. The current just glides through. But an insulator like glass, its resistance is trillions and trillions of times higher. It's like a brick wall for electricity. The flow just stops dead. And this is where it gets really clever, and you see it in your house every day. We use something with super low resistance like copper for wiring because we want the electricity to move efficiently. But sometimes we want that resistance. Think about a toaster. The coils are made of an alloy called nichrome, which has high resistance. That electrical friction is what makes it glow red hot and toast your bread. We actually harness resistance to do work for us.
So there you have it. The flow is the current, the push is the voltage, and the squeeze is the resistance. It's a simple, elegant set of rules that runs our entire world. Now that you know the secret, what are you going to do with it?